Okay, so we are talking about determination of analyte amounts, and see if we can remember what an analyte is in the first place. What's an analyte, Pablo?
It's stuff in liquid.
Yeah.
Like as we pour.
Yeah,
Yeah.
but there could be a lot of stuff in there, though.
It's the stuff
It's the stuff
you want.
you're interested in. Like it could be the caffeine in Pepsi, for example, right? There's a lot of other stuff, but your analyte's caffeine. Okay. And then when you get the amounts, another word for it is quantitative. So quantitative analysis, amount. What's the type of analysis, Randy, that they call it when you're after the type of compound, not the amount? Oh, is it caffeine or not? That's not quantitative. That's, what'd you say? Qualitative. That's qualitative, right? Equation for a straight line, right? What is that stuff, Sandy? The y equals mx plus b. Where does all that stuff go? What's the slope? Oh, not both of them. Just the m, right? The y-intercept, right? So in this case, if this doesn't look very linear, what if you do a regression analysis? We'll talk about that later. Get your straight line going through there. It looks like the y-intercept would be positive or negative on that, Anna. That y-intercept. Right? Here's 0. So it's going to keep going. Where's it going to cross the y-axis? It'll be a positive number or a negative number. It'll be a negative number, right? Is that a problem? Well, who cares, right? The point is that you want it to be straight. Okay. All right. Y-intercept. So all that makes sense if you, right, have your y and your x there. And there's error, right, in pretty much every measurement you make. What are these mathematical little symbols? Kathleen, what are those? Yeah, which one is the mean? It's the x bar. Yep. Yeah. It's the theoretical, or the, you're right. It's theoretically true, right? Sometimes you know what the real true answer is, but very often it's theoretical, right? So this absolute error, EA, is equal to ER plus ES. John, what the heck is this? ER and ES? There's two types of error. The hints are the one starts with an R, the other one starts with an S. No. Ran. What? Oh, so close. Random. Bouncing all over the place. We saw a lot of random noise last class period, right? The noise bouncing around the oscilloscope. Systematic, right? How can you tell the difference between the two, Alice? Yeah, but what does systematic mean? Random makes sense. It's bouncing all over the place, but how do you know you have a systematic error? Yeah. It's the one you can fix because the answer is always too high or it's always too low. You turn some knob or turn some, right? You're going to fix it. So systematic is the one that you really have a shot on fixing. Okay. And then there's another equation, percent relative error. Okay. So times 100 to get into percent. We've got some calibration curves. Here's one. And it's kind of blown up what you had. All right, this one blown up. Do they have to be linear? Adriana, do calibration curves have to be linear? Well, I guess, I don't know. Either way, I mean, are you always going to get a linear calibration curve? Does everything always respond linearly? I mean, this guy, if you look at him, and if you had to go to a court of law, or if you're really putting money on this, or someone's dosage, I would not say that's a straight line, right? You can definitely tell there's a curve there. So which one would be easier to make? If you're the dude making these curves, a linear or a nonlinear calibration curve? Linear one, most definitely. Look at all the points you need. If you didn't have that many points, you couldn't even tell that had a curve. So nonlinear is a heck of a lot of work, right? Okay. Dynamic range. Now we're getting into the area of they're trying to sell these instruments to you. Yes, Ashley.
So they don't have to be linear.
Well, you don't have a choice. Either they're linear or they're not, right? And if it's not linear, you just have to work with it and get a lot more data points to characterize that curve. Right? It could be either one. Yeah. Because not everything responds linearly. Like this machine or whatever that analysis that is. It might be chemical. That's why it's doing that. But dynamic range. Ooh, this instrument has a dynamic range over 5 orders of magnitude. What does that mean? Because if you had a choice, you want it to be what type of calibration curve? Linear, right? So that just means, man, this instrument is linear over, like from this signal all the way to 1,000 times larger. It's linear over that entire range. Ooh, I want that instrument, right? Because life is going to be so much easier. Oh, our dynamic range isn't as big. Well, then maybe it's a cheaper machine for some reason. Okay, so we are really hoping that things are responding in a linear fashion. Otherwise, we can't even use this equation, right? Because the big goal here is y is your signal, right? X is your, in a calibration curve, what would be the X? Not time. Signal versus concentration, right? Signal versus concentration. So you plug in, so you make all these standards, right? And you get the signal, and you get all this data. And then you plot it out, right? And hopefully it's linear. And then you get your little m and your little b. All you do is you go to data analysis, regression analysis, and you've probably done this before. You can use any kind of software. It all works, Excel or graphical analysis, right? But the point is you want to get this little m and this little b. And then you have your unknown. Well, here's an example, right? Here's my stock. Here's my unknown, right? Lighter blue. Have all these. I'm going to make 4 standards, right? How do I make a standard concentration? What equation do you use? I know my stock. MIVI equals MFVF. So here's your MI, right? And just pick an MF, right? Use the equation, get your VI, suck it out of here, put it in here, put it in your container, fill it up to the mark. That could be your VF. You're going to be doing that a lot in lab. Okay? And then you make all your standards, put them all in the machine. Here's all your concentrations. Put them in the machine, get all your signals, plot it, get your little m and your little b. Then you put this guy in the machine. Get a signal, and then you can calculate what? The concentration, right? That's how you always do it. You don't do it this way. Oh, here's my signal of my unknown, and then do a little ruler thing. No, right? Plus, no one does this by hand anyway. It's all done on you're sitting there on the computer screen. So you calculate it. Plus, the odds are you're never going to fall on one of these data points. You're always going to be somewhere in between. So you calculate it. And that's what we'll be doing a lot in lab. Okay. Very easy for me because I make up an unknown. And if you get the right answer or you don't, that's everything. Because if you get the right answer, that means you know how to use the machine, right? You know how to make solutions. Oh, whole gambit. So to teach this class is pretty easy for the lab part. I just make an unknown and then I give it to you. It's all up to you. Okay, so that's pretty much what the lab practicals are going to be like. Okay, but you've been through that in analytical, so let's see. Where are we? Okay, so this term dynamic range just means this guy's valid. Your little m and your little b, you can plug in the signal number and calculate the concentration. It always works over that range. That's the dynamic range. So it's a good idea to know if you're inside the dynamic range. And there's an easy way to tell. I don't know, it's a hard question though. How could you tell? If you double the concentration, what should happen to the signal? If it's responding linearly, it should double. Halve the concentration, the signal should halve. That's the easy way of telling. Okay. So that may not quite be the case with this plot, because look, he's not linear. Double the concentration, he may not double. Okay, the other thing you got to be careful on is, and I'll nail you for this, right? There's my signal range. I'm looking at these two endpoints. Oh no, here's the one up here. That one and this one. So right there and right here. This is my concentration range. This is my signal range. If your unknown is outside of that signal range, you can't use that calibration curve. Because you're assuming then, let's say it's way up here. You're assuming then that this line is linear, right? Which is probably okay, but it's not good practice. So your signal, or right, it always has to lie within your concentration range. Okay. Otherwise, it just, people are going to frown on it. Okay. Let's see. Okay, so there's three types of external standard calibration curves. This is external standard calibration curve. You just make up these standards. You have a stock, and then you do the MIVI equals MFVF to make up your standards. Right? Plot them all out. That's external standards. We just usually call them standards, but external standards. Emily, if I flip this around, before it was molar, now it's ppm. Do you remember what ppm is? This is 700 ppm. What was ppm? It's parts per million, but that doesn't really help you make solutions. It's like big M is moles per liter. That helps. What's ppm? Ooh, she's got a good memory. Milligram per liter. That's what ppm is. Yeah. Okay. Single point calibration curve is the first one. Single point. Doesn't seem like you get a whole lot out of that. That's a calibration curve, so it has to be signal versus concentration, right? I mean, what the heck? Single point. All you do is pretty much, I call it a response factor. I think the book did too, but I'm not so sure anymore. It's easiest to think of it this way. Right? Get a response factor. So all you do is you make up one standard, get its signal in the machine. Divide the signal by its concentration, you get this little k. And then you just shoot anything you want. Get your unknown, measure its signal, and then calculate what? Calculate the concentration, because you know what the little k is. Just assume k never changes. It's kind of like the slope idea. So you make one standard, measure its signal, divide the two, and get this number. We'll call it the response factor, k. And then you take whatever unknown you want, right? Put it in the machine, get its signal, and calculate CA. So, I mean, there's a lot that could go wrong there, but it's pretty easy. And if you get paid by the hour, that wouldn't be a very good deal. But if you're the dude paying the dude, that'd be better. Multi-point calibration curve. So you have your signal, your concentration. You have to make up a whole bunch of standards, right? Make up a whole bunch of standards, external standards. Measure all their signals. Plot it all, right? Hopefully it's linear, right? And then you use your y equals mx plus b. Your signal equals m concentration plus b. Right? So just plot it out, kind of like what we did before, we talked about before. Make up all your solutions, plot it out, get your little m and your little b, and then you just shoot your unknown. And get what when you shoot the unknown? Get the signal and calculate your CA. Right? Okay. Okay, so you'd think that would be enough. But life is more complicated, yeah. It's got some complications in it. Okay, here's one. Internal standards. We were talking about external standards, now we're talking about internal standards. Ashley, what's this internal standard stuff? What was it? Anybody know? Okay, there's a problem. You start talking about a lot of these fancy machines upstairs, you can fork out a lot of money, like 65 grand for a gas chromatograph mass spectral detector. But you can only, our engineering is only so good. For example, you want to sample a gas, because that's gas chromatography, right? You're sampling a gas every single time, and then you're putting it through the detector. Sampling a gas is really hard to do the exact same volume, the exact same amount every single time. It's really, really hard to do. So picture it this way. You know, what is it shooting through the machine, right? Maybe it's whatever fits in this box. This time it gets 3 molecules. Next time it gets this amount. And you shot the same standard. See the problem? You shot the same standard. You better get the exact same signal. But you're sampling a gas. It's really, really hard to do. So if it's and there's so many analyses depend on this kind of stuff, especially in the forensic science lab. So if you're going to sample a gas, so how do you solve it? You can't fix it engineering-wise. We just don't have the solution there. You have to fix it internally, internal standard. So what do? You find, so X is our analyte, right? This is what we're sampling. We're just going to mix our little, you're going to make those little standards again, but inside that little bottle, right, of your standards, trying to draw a volumetric flask here, right? I've got my X in there, but I'm also going to add my internal standard. I don't know, let's call it a little B or something. Other molecules. Okay? So that's my X is my analyte. So I just have another solution, this internal standard. I just spike it. Just add some in here, a known concentration. Keep it constant in all my standards. Okay? So I'm not going to change the internal standard concentration. I just want to just fix it. Make it, I don't know, 0.1 ppm in every single external standard I make. Let's add 1 ppm internal standard. Fine. Okay. So all these standards now have my analyte and my internal standard. So we call these internal standards now. So that means when I shoot this into the machine, I still sample different amounts. So in that top one, he didn't sample enough. That means I won't sample a whole lot of internal standard either. The bottom one, the machine sampled too much. Well, that means I'm going to sample too much internal standard too. Okay? So when you make these plots, you're not going to plot just the signal of your analyte versus concentration of analyte. You're going to plot the ratio. Signal of the analyte to the signal of the internal standard. It's twice the amount of work because you have to make 2 measurements. You have to measure the signal of your analyte and the signal of your internal standard. So you're going to get like two little peaks or two numbers, whatever the machine's reading. You divide those two, and that's what you plot out, and that makes things nice and linear if it's a linear relationship. Otherwise, it's not going to be linear. They're going to be shooting all over the place, okay, due to sampling fluctuations. That's really the technical jargon for this. When this is going on, you have to use internal standards. And that's really for the GC is big on this. Okay. But you're going to find out in lab, you've got so many other things to worry about, and we're not going to a court of law or anything. I think we only use internal standards once on the GC. After that, we kind of just, we know we should, but we don't. Kind of like the whole sig figs thing, right? We did that once, and then you kind of just, okay, 3-4 digits, whatever, right? Just kind of match whatever else you're using. Okay. Yeah, we'll skip this. We'll make this, some homework. Okay. So it'll be good practice. So you can use whatever software you want to make that calibration curve. There's Excel, there's graphical analysis, there's on that computer over there. Okay. Excel's easy. I would just, and if you have trouble figuring out how to get the little slope in the y-intercept, right? Just ask. I can help you out to show you where regression is and things. Graphical analysis, I think, is the easiest one to use. But okay, we're almost done here. Okay. What is a sample matrix? Sir McGee, what is the matrix?
Oh. I have no idea. I'm going to take the shot in the dark and say, take a sample, you get enough values, put it in.
Anybody know? We had it in analytical. Everything surrounding the analyte. Here's an unknown. Everything surrounding the analyte is just water, and I know that because I made the unknown. So this is a very, very simple matrix, one that's very easy to reproduce. So you just go in and you make your external standards, right, using the stock solution of the stuff. And then you dilute it up to the mark with water, because that's what this stuff is. You're diluting it up to the mark with the matrix, because it's everything surrounding the analyte. It's exactly reproduced, right? The exact same matrix is here as it is in here, as it is in here. It's constant. You can't screw up your analysis. What if this was your sample? That's from Elmendorf. What if this is your sample? You want to know the amount of caffeine in Pepsi. Yeah. Well, the label's gone. Or you want to sue the guys. Yet your sister had a heart attack, and you think it's because of an overdose of caffeine or something. Right? You keep millionaires. But see and then just imagine, you put this through a machine, and maybe you got it figured out how you can respond to the caffeine somehow. Maybe. There's a lot of different machines we're going to talk about. But the point is, what if the machine also measures, there's a lot of stuff in here, right? How do you know you're just getting a caffeine signal? Like over here, I don't know, some dude dumped, what was that? I forget her name, but like chromium. Chromium was the big thing in the environment, and remember there's a movie on her? Anyway, someone dumped some chromium in Elmendorf. And you want to, I think hexavalent is if I remember this right, that's the really, really nasty stuff. Well, you want to figure out how much chromium's in here so you can go sue whoever, right? So they can clean it up. There's a lot of stuff in here. Yeah, you can do the whole fancy vacuum filtration and all this stuff, and you think it's a nice, clear solution, but there's a lot of other stuff still in there. How would you, because you want to run it, so you want to, in your standards, you want to exactly reproduce the matrix, is the point. That's the whole standard has to exactly reproduce the matrix, otherwise your whole analysis is off. You have no idea what you're measuring. You have to reproduce the matrix in your standards. You have to. You have no choice. Okay. So what is an external standard calibration curve? That's everything we've been talking up so far. You exactly reproduce the matrix in these things because it's just water in the first place. Really easy to do. Will an external standard calibration curve give incorrect results in something like this where you can't reproduce the matrix? You bet. I mean, odds are, you're not sure. I mean, you might get it right, but you don't know, right? Okay, so when should a standard addition technique be used? This kind of stuff, right? Real life. You can't reproduce that matrix. Why even try? It would be a PhD thesis and more to figure out everything that's in here. And you don't even care. All you care about is the analyte, which is hexavalent chromium. Or caffeine in here. Okay. So how is it done? Oh, by the way, looking at that Pepsi, this is another research project I'm thinking about. FDA just published this. All these dudes report the amount of sugar. But they're all way, way off. Sometimes upwards of 60%. So that's a lot. So it would be interesting and it's not a very simple analysis. Because separating sugars out isn't very, and you can't use the GC because around heat, what happens to sugar? Just gunky, caramelizes. So you can't use that. You have to use the HPLC. But anyway, it'd be kind of interesting to figure out a method how to separate the sugars out and see who's lying and who's lying, right? But anyway. So how do you do this standard addition technique? There it is. Okay, you have an unknown sample, having your analyte, so that could be like the jar of Elmendorf, right? Then we've got a bunch of these volumetric flasks, right? And they're all up there. And then we have our stock solution of our analyte. So maybe it's the blue, for example, right? Get rid of some of this stuff. This is really hazardous dye. Most colored things are really hazardous, by the way. They're carcinogenic. But we got this really hazardous dye. That's just food coloring, though, so that one's okay. And someone dumped it in here, and you want to find out how much there is. So you need to know what your analyte is and have a stock solution of it. But the matrix definitely isn't reproduced, so there's a problem. Okay, so what do? What you're going to do is you're going to, I don't know, call these flasks 1, 2, 3, 4 or something. Otherwise, it's hard to distinguish them. Oh, they are numbered. Yeah, all right. So in flask number 1, we are. Oh, first, let's do this first. First, what's the symbol for it? So into each flask, we're going to dump the unknown. We're done. Matrix is reproduced. Because we have the exact same matrix in every single one of our standards, just by putting in the unknown. Okay? So we put in and you only have a 25 ml flask, so you got to be careful here, but I think the more unknown you can fit in there, the better, right? So you put the same amount of unknown in each one, and the next thing you do is you spike each flask with some of this stuff, some of your stock, right? I think this is a personal thing here. For me, this first flask I don't spike, right? But these I spike, the next ones. You put in some VS, right? And VS is your stock, right? So second, add VS to, I'm going to say numbers 2 through 4, but a lot of folks just do them all. Okay. Now the reason why I leave out flask number 1 is that when I put this guy in the machine, it makes me feel a lot better if I can see a signal. Right? Because otherwise, we may be way below the detection limit of our instrument. And you'd never know it if you spike it. Then you get this nice result of these analyses, and you're saying all. One thing about science is if you're a scientist and you say something, if you're not another scientist, which is most of the rest of the world, everybody believes you like it's a Bible, right? So you got to be careful. So I don't spike. I think it's a very good practice not to spike this one. Get a signal so you know your machine is reading it. Okay? Good deal. And then you spike all the rest of them. And then you plot everything out. Get signals, right? Get your signal. Put each one of those in the machine. Get a signal. So then you have to plot it out, right? Your signal. But you plot it versus the volume of the stock you added, right? So your very first data point is going to be 0, because class number 1, you didn't add anything, right? Hopefully you get some signal on it. If you don't, I would say you got to find a different technique. And then your other 3, hopefully it's nice and linear. If it isn't, this whole thing's not going to work. It's not going to work because look at the theory. You have a little b and a little m. So it's assuming there's a linear relationship here.
So you're adding a different VS to 2, 3, 4.
Yeah, just spike it more and more and more. Okay, like 1, 2, and 3 mils or something. And in the lab, there's some suggestions on how much to spike it with. Because then you get a prettier plot. Just like some folks are doing, I don't know. Yeah, some folks already did standard addition technique. And there's a little equation that tells you how much to spike. You don't have to do that because all you're plotting it versus the volume of the stock. But it looks nicer if you do actually use the little relationship to tell you how much to spike. But you have to know how much is there in the first place, a rough idea. But anyway, so you plot it out, do the regression analysis, find your y-intercept, find your slope, plug it all in, right? Vx is your aliquot, right, that you started out with in the first place, right? B and M. What's CS of the spike stock solution stuff? Yep. What's CX in what? Notice this is where I think it gets confusing. It's your concentration of your unknown, yes. But you realize you have 2 solutions here. One is this one, right? Because you put in your aliquot, then you diluted it up to the mark with water or something, right? Because in the end, you had to dilute it up to the mark. First dump in Vx of the unknown, add some Vs. There should be a number, third step, dilute it up to the mark, right? With water or whatever your solvent is. Third, dilute to mark, right? Okay. Now what I was getting at is this concentration from your unknown, right? There's your unknown sample, then you have the concentration unknown in here, right? Because the concentration of the unknown, right? Which one is it? It's the concentration of the unknown in that aliquot. And that aliquot was obtained from here. So yeah, it's a concentration in that big beaker of Elmendorf, or whatever it is. Okay, so it's your answer. It's your final answer. There's no dilution factors or anything that you need to worry about. Oh, that's it. Okay. So I would have a rough idea how to explain this mess, right? Okay. I think the hint I would be giving you on the quiz would probably be just how it looked without all the writing on there, right? I'd give you this, that, and this, and then like the diagrams, and then you just have to say the steps and what you do. That would be your hint. It's kind of a hint, right? It's kind of a hint.